Hello guys, good morning. Good morning to all of you. How are you all? Morning to all of you. Can you hear me properly? Is everything all right? So today in this session we'll be discussing the second part of the mathematical tools of quantum mechanics. Understanding mathematical tools of quantum mechanics is very important because without that we will not be able to tackle quantum mechanics. So that is why we are taking it in multiple parts so that you understand it better. On the last class we introduced bracket notation and all. In this session we'll be talking about the operators. Operators are really very important tools in quantum mechanics. So let us start with the definition of an operator. Before that, let me know if everything is all right. Okay, let me check. What is an operator? Okay, let me check. Okay, from my side it is okay. You see, an operator is always written with a hat, cap. A cap is a mathematical rule that when applied to a ket psi, transform it to another ket of the same space, and when it acts on a bra, it transforms into another bra. So prime denotes it is another ket or it is another bra. A psi prime, and you see this operator acts from left on the ket, and here the operator acts on the bra from right, you can see. So there is a slight difference here. Now let us talk about some examples of the real operators. So unity operator. Unity operator means it will leave the things unchanged. First of all we'll talk about unity operator. What is this unity operator? It leaves the ket unchanged. It leaves the ket unchanged. Means if you apply it on some ket, let's say identity operator denoted by I cap. If you apply it on some ket psi, let's say this ket will remain unchanged. So this is the unity operator. Let's talk about the gradient operator. There are some examples how operator works. Let's talk about the gradient operator. So you all know this. It's a gradient of psi r. So what is this gradient operator? Del psi by del x, I cap, del psi by del y, j cap, del psi by del z, k cap. So this is the gradient operator. Let us now talk about the linear momentum operator. Linear momentum operator. This is very much used. Linear momentum operator. It is denoted by P of psi r minus I h cut del psi r. If you consider it in one dimension, it will become del x. Let's talk about the Laplacian operator. Laplacian operator, you all know about it, you have read it in electromagnetic theory. Laplacian operator is denoted by grad square psi r. So del square psi of r you can write, or you just simply write psi by del x square plus del square del y square del square psi by del z square. So this is the Laplacian operator. Let us take another example, that is parity operator. The parity operator. What does this parity operator do? Parity operator, while acting on some wave function, it just reverses the sign of r. So from psi of r, it will become psi of minus r. So this is the function of a parity operator. So I hope you got the pretty much idea about some of the operators. Let us now talk about product of operators. What about the product of operators? Look, the product of two operators, they do not generally commute. Product of two operators do not generally commute. What does it mean? It means, let's say we have an operator A, an operator B, so their product AB is not equals to BA. However, the product of operators is associative. The product of operators is associative. So we have already defined what is this associativity. Let's say we have the product of three operators A, B, C. So you can write it A times B times C, or you can also write A, B, C. This property is known as the associativity. Now let's say we have A to the power n and A to the power m. These are all operators. So we can write as usual A cap to the power n plus m. Now let's take an example. If we have a product of operator, let's say AB. Now this product of operator AB is operating on some kate psi. Good morning, Murli. Now when this product of operator operates on psi, how does it work? You see, it will work in this way, that this part, the second operator, will work on it first, and whatever be the result, that will be applied by A on that. Okay. The order of application is important. It is not like you apply A first, then B. The order is important. First B will apply. So B will apply on this kate psi. It will convert into some other kate, and then A will be applied on that modified kate. So it is like if you have AB applying on kate psi. So this will be first B will be applied on that kate, and whatever be the result, that will be acted upon by A. Now let's say you have the product of multiple operators A, B, C, D. operating on, let's say, psi. Then what will happen? First, D will act. Okay, first D will act and produce some kit. Then C will act on that kit. C will act on that kit. Then B will act. On the produced kit. Then finally A will act and you will get a final kit. Okay. So order is important. It is applicable from the left, so rightmost operator. So I hope you got the product of operators thing. Let's go for linear operators. What do you mean by linear operators? This is a very important thing. Linear operators. If you have any question, you can ask instantly. What do you understand by linear operators? So let's go for the definition. If you have an operator, let's say A, it is said to be linear if it obeys the distributive law. Distributive law, and like all operators, it commutes with the constants. The second property is common for all. The first property is the main property. It should obey the distributive law. It commutes with constants. Okay, then it will call the operator to be a linear operator. So what is this thing, distributive law? Let's say we have an operator A. If this is linear, and let's say A1 psi 1 plus A2 psi 2. So it is applying on this state. So it will follow the distributive law, means this will become A1 A cap psi 1 plus A2 applying on psi 2. And on the other hand, if you apply it on some brass, then what will happen? Let's say psi 1 A1 plus brass psi 2 A2. On the bra, operator will be acting from the right. So this will become A1 psi 1 A cap A2 psi 2 A cap. So this is how a linear operator works. These are some examples. Now there are some remarks on this context. On this occasion, we can define the expectation value. The expectation or mean value of this operator A. So we represent it by writing it under the two arrows. Mean value, let's say, of an operator A cap. This mean value or expectation value of an operator, we must define it with respect to some kit. So with respect to some kit psi, with respect to a state psi. How it is defined? Is defined by, let's say, A cap is equals to psi A psi divided by psi psi. So this is a very important formula. The expectation value of an operator, with respect to some state psi is defined in this way: psi a psi divided by psi psi. This one you will remember, this will be applicable, this will be used many times. Now let us take an example of the linear operator. If you have the quantity like this, ket phi and bra psi, product of a ket with a bra, the product of a ket with a bra. So this type of thing is a linear operator. It is a linear operator in the Dirac notation. Okay, to verify this, let's apply it on some ket. Let's say phi psi. This as a whole is a linear operator. Okay, we are applying it on some ket, let's say psi prime. We have applied it on some ket psi prime. So you see, this will become psi prime phi. Can you write? You see, this psi prime, this becomes a scalar product, so we can take it as a constant, and this ket phi was there, so you can see it is behaving like a linear operator. So this psi prime, this is a scalar product, so this will give you a complex number. So we can say that this phi, product of a ket with a bra, this whole thing, it is a linear operator. And one thing I would like to mention here, that if you get terms like, let's say, ket, if you apply like this, this is not allowed. Okay, this is not allowed. On the other hand, let's say if you apply the operator on a bra from the left, this is also not allowed as per bracket notation. So you must remember this. They carry no physical significance. Let us now talk about Hermitian and skew-hermitian operators. So many of the terms will be very similar to what we have learned in the matrix in mathematical physics. Okay, Hermitian and skew-hermitian operators. Let's say if you have an operator A, let's say it is said to be Hermitian when if it is equal to its adjoint a dagger. These are all operators, so a cap must be given. Mathematically you can write, if A is equal to a dagger, then A is the Hermitian operator. Or in terms of, with respect to a wave function, if you write expect this operator. So it is psi a, let's say phi. This is phi a psi dagger star. This is the meaning of A is equals to A dagger. On the other hand, if it is a skew-hermitian, let's say an operator B, it is said to be skew-hermitian or anti-hermitian. Under what condition? If B dagger is equals to minus B, or you can write it in this notation, psi B, let's say phi, this is equals to minus phi B psi star. So these are some simple definitions. A is equals to A dagger, it is Hermitian. And let's say A dagger is equals to minus A or B dagger equals to minus B. This defines the skew-hermitian operators. Let us take a problem. I am giving a problem. Let's say discuss the hermiticity of the operators. So whether they are Hermitian or skew-hermitian. First one, A plus A dagger. Second one, I times A plus A dagger. And third one, I times A minus A dagger. So you have to tell whether they are Hermitian or skew-hermitian. Let's say B, operator B is denoted by A plus A dagger. Now if it is Hermitian, then what we have to do? You have to check B dagger. B dagger means A plus A dagger whole dagger. Now look, what does it give you? This will give you A dagger plus A. So this gives you back B. So we can say that A plus A dagger is a Hermitian operator. Okay, the first one is done. Let's go for the second one. I times A plus A dagger. Will it be Hermitian or anti-Hermitian? This will obviously be anti-Hermitian, because I, when you take dagger, it will become minus I. Okay, and this will remain same. Let's say if you consider let's say it is C. So what about C dagger? C dagger will be, I am just writing it directly, minus I times, you will get back your A plus A dagger. So that is minus C. So this one is anti-Hermitian. Let's go for the remaining one, I times A minus A dagger. What it will be? Will it be Hermitian or anti-Hermitian? Let's say this is D dagger. So let's say this is D cap. So D dagger will be how much? You see, this is minus I, A dagger minus A. So you can write it I times A minus A dagger. Can I write it? Yes. So this gives you back D. So what does it mean? It means this is Hermitian operator. Yeah, first one is Hermitian, second one is anti-Hermitian, and third one is again Hermitian. I hope you have understood the basic idea of checking Hermitian and anti-Hermitian. Let us now go for projection operators. This is one of the very important operators we deal in quantum mechanics, projection operators. So let us go for the definition first. If you have an operator, let's say P is said to be a projection operator if it follows certain property. If first of all it should be Hermitian. This is the first criteria, that it should be Hermitian and it is equal to its own square. Look, the second property along with the first one is quite necessary. The first criteria is to of a projection operator that it will be Hermitian. Hermitian means P dagger is equals to P, and the second one is square of the operator should be equals to that operator. So these two property should be fulfilling for an operator to be called as projection operator. The simplest example is the identity operator or unity operator. Unity operator. So why this is a projection operator? Because you see, if you take I dagger is I, so this is following the first property. On the other hand, I dagger I square is again I. So unity operator, identity operator is a projection operator. Now there are certain properties of projection operator. Look, these are the two main properties, that is okay, but some combined properties are also there. Whether sum of the two projection operators is also a projection operator, or the product of two projection operators is also a projection operator, and all those stuffs. So let's give this heading properties of projection operators. So what does the first property says? The first property, the product of two commuting projection operators. Do you understand the term commuting? What do you mean by commuting? Murli, do you know the meaning of commuting? So let's say the product of two commuting projection operators P1 and P2 is also a projection operator. Why? Because you see, let's say we have two projection operator P1 and P2. So we have to check these two properties. Simultaneously measurable, yeah, that is one thing, but let's say commutation of two thing A B is equals to A B minus B A. If it is 0, then you can say that A B are commuting. Under this situation, A B can be simultaneously measured, means the error in measurement will be 0. So this is the meaning of commuting, means the commutation of AB should be 0. So AB will become BA for commuting operators. Okay, this is a side note you can add if you do not know. So P1, P2 are commuting projection operators. Now let us say P1, P2, whether it is itself a projection operator or not. So to do that, we have to check the first property, that is the dagger of it should be equals to that operator, means we have to check the hermiticity. So you see, this is this dagger will act when you are acting on a product, it will act from the right. So first it will act on P2, then it will act on P1. The order is important. You see, for a product it will be applied from the right, not from the left. So P2 dagger is P2, P1 dagger is P1. Because they are P1, P2 itself are projection operators, so they must be Hermitian. So that is why P2 dagger is equals to P2, P1 dagger is equals to P1. So this is the first criteria we have checked. What about the next criteria? P1, P2 square of it. So you see, we can write it twice, P1, P2, P1, P2. So what will be this value? Again it will be P1 into P1, so P1 square, P2 into P2, P2 square. So P1 is square, because P1 is a projection operator, so P1 P square must be P, so P1 square must be P1, P2 square must be P2. So it is following the certain properties of the projection operator. So we can say P1, P2 is also a projection operator. What about the sum? Sum of two projection operators. It is not generally a projection operator. It is generally not a projection operator. The sum is not generally a projection operator. Now if you have two projection operators, when under what condition they will be called orthogonal? Two projection operators are said to be orthogonal if their product is 0. That is the basic definition of orthogonal. These are very straightforward rule. Now what are the condition? What is the condition under which if you have a sum of projection operators, it will be eligible for being called a projection operator? So for a sum of projection operators, let's say sum of P1, P2, P3 and so on. If you want to call it a projection operator, what criteria it should follow? It is necessary and sufficient that these projection operators should be mutually orthogonal. These projection operators should be mutually orthogonal. What does it mean? That is, the cross term must vanish. So you can imagine it in this way, that Pi, Pj equals to 0. Okay, I not equals to j. So this defines that they are orthogonal, mutually orthogonal. If you take, let's say, the product of P1, P2, it will give you 0. P2, P3, it will give you 0. P3, P4, it will give you 0. So if this criteria is satisfied, we call it to be projection operator, the sum to be projection operator. Now there is a very interesting question based on these projection operators. So the question is something like this. Look, these questions, this part is very much useful if you are tackling an interview. So we have to show that the operator. So we are defining the operator from the bra and ket. This is a ket psi, bra psi. This operator, you have to show it to be a projection operator. And this will be projection operator under one condition, only when psi is normalized. Psi is normalized means the scalar product with itself should be 1. That is the meaning of normalization. So we have to show that this operator ket psi, bra psi is a projection operator only when psi is normalized. Can you show this? So to be eligible, to be called to be a projection operator, the first criteria is to you have to show it to be Hermitian, right? So it is very easy to show. How can you show it Hermitian? Let's say this operator psi, ket psi, bra psi. If you take dagger, what will it become? This will become ket psi and this will become bra psi. So we can say this is Hermitian. Now the next property, you have to take the square and you should get back this. So to prove the next property, we are taking square of it. So if you take a square, squaring means writing it twice. So we have written it twice, and as you can see, this is psi, 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 psi. Now you see this portion, if psi is normalized, this is 1. So we can write this to be psi psi if psi equals to 1. Sorry guys, that is ket psi is normalized. So, very standard proof. So, the product of the cat's eye with the brass eye is a projection operator. Is there any question till now? I hope not, because these are very interesting and easy topics. So, you should not get it very difficult. Although we have already introduced commutating or commutator, let us separately talk about this commutator algebra. Commutator algebra. Square one, please explain. So, you know this second property, that the square of it should be equals to that operator to be eligible for becoming a projection operator. So, square of it, so we have written it twice. Okay. So, this remains as it is. Now, we are just combining. So, this cat's eye is coming with it, this brass eye and this eye. Now, if you look at, this is the normalization condition, and this is a norm of psi. So, if this norm of psi is 1, then what is left? This cat's eye and this brass eye. So, that is what we have written. If this norm is 1, then only the square of it is equals to that. So, when norm is 1, when psi is normalized. You can write it in this way. This is the way of writing. These brackets will vanish. Okay. This bracket just to show that we have written it twice. Now, this and this combines into one line. Okay. So, it can be written in this way. Commutator algebra. So, what is the commutator of two operators? Commutator we have already defined in matrix also. Commutator of, let us say, two operators. Commutator of two operators, one is A, another one is B. It is defined by commutator of AB denoted by and defined by commutator of AB is equals to A cap B cap minus B cap A cap. Simple as that. Now, there is something called anti-commutator. The anti-commutator is represented within second bracket. Anti-commutator of AB, anti-commutator we represent it by within the second bracket, is defined by A, B. What is the difference? Instead of minus, there will be a plus sign. Okay, this is the anti-commutator. Now, when we call that two operators are commuting, two operators are said to commute if their commutators is equals to 0. If their commutator is equal to 0. And if commutator is equals to 0, what we can write? We can write AB equals to BA. If I talk about any operator will commute with itself. Any operator commutes with itself. What does it mean? Let's say you have an operator, let's say A, so it will definitely commute with itself. Now you note that if two operators, look, these bullet points are very important. If two operators, let's say they are Hermitian, means the dagger is equals to that operator. If two operators are Hermitian and their product is also Hermitian, so if you have a set of operators which are itself Hermitian operators and the product is also Hermitian, then these operators will commute. These operators will commute. Let's say A, B. What is the criteria for being commuted? A, B, dagger. You see, it will act from the right. So this will be B dagger, A dagger, B dagger, because these operators are Hermitian, so B dagger is equals to B, A dagger is equals to A. So from AB dagger is equals to, from AB dagger you get BA. And on the other hand, since AB dagger, product is also Hermitian, so AB dagger means what? It must be equals to AB. So AB dagger is equals to BA, AB dagger is also equals to AB. Therefore, what we can write? AB equals to BA. So writing AB equals to BA means what? They commute. A and B commute. So it's a small proof that if two operators are Hermitian, their product is also Hermitian, then they will commute. Okay, try to understand the last one. Let's be back. The flower bucket is called Poisson bucket. Now that is in classical mechanics, okay. we'll talk about it. Poisson bracket, we deal in quantum mechanics, sorry, classical mechanics. In classical mechanics also, for denoting Poisson bracket, we use this symbol, but this is not the same here. Let us now discuss some of the properties of commutators. This is very crucial because many of the problems we'll deal with will be done by this. Look, I'm giving sufficient time in the mathematical tools portion because this is like the base. You are building a house, base must be strong. So if your mathematical tool becomes very strong, then you can easily handle quantum mechanics problems. So if possible, try to revise also. Properties of commutators. First property is the antisymmetry property. Antisymmetry. What is this antisymmetry property? So if you have the commutation of AB, let's say, so this is not equals to commutation of BA, rather it is negative of BA. So this is known as antisymmetry. If there is no negative sign, you could have said it is to be symmetry, but it is antisymmetry. Commutators are antisymmetric. Next, linearity. Linearity. So let's say you have the commutation of A and B plus C plus D. So this will operate in a linearly fashion. So A, B, the way you have seen linearity, then plus commutation of A, C, then commutation of A, D. This may appear to be very straightforward, but this is what it is. Like if you ask class 5-6 students what is second law, he or she will tell you F is equals to ma. So for to him it may appear to be very much straightforward, but you imagine when it was being discovered by Newton. At that time it was not so much evident. Okay, so it is just about the perspective we have today. Hermitian conjugate. Hermitian conjugate of an operator. Hermitian conjugate of a commutator, sorry. So if you have commutator of AB, let's say, Hermitian conjugate means taking this dagger. So this will become B dagger A dagger. Okay. It acts from the right. Another property, distributivity. Distributivity. Too much difficult word. Distributivity. Now this distributivity property is quite widely used. A, let's say BC. What is this commutation? What does this commutation give you? You should remember one thing. BC is at the second term, okay, and from the second term, B cap is at the initial position, C cap is at the later position. So B cap will come first, B cap, then A, C. Okay, this one you try to understand very carefully what I am doing. Then you have to keep B and take out C. Now C is at a later position, so it will come out to the right of it. What do I mean? A is unchanged. We are keeping B. We have to remove C. So don't place C here. Rather, C will be placed here. B is on the left. So don't write B here. B should be written here. C is at the right, so C will be written here. So simple thing, but you must keep in mind. For example, let's say A, B, C. A is initial, so A will come out to the left. If it is at left, it will come out to the left. If it is at right, it will come out to the right. So we are keeping B and C is fixed. Now if you want to keep A, take out B. So what will you write? You will write A, C, B will come here. The very fine things. On this note, there is a Jacobi identity also. Jacobi identity, you must have seen this kind of word in classical mechanics as well. But here in quantum mechanics, we deal with this quantity which are operators. So the Jacobi identity is given by A, B, C. So it's a cyclic thing. Okay, if you remember this cycle, then it will be very easy for you to remember the Jacobi identity. A, then BC, commutation of A and commutation of BC, plus you take B, then CA, B, then CA, then C, AB. The sum of it is 0. This is known as the Jacobi identity. Another very straightforward property that operators, we have told you that operator commutes it with itself, and another property that operators commute with any scalar. Operators commute with scalar. Let's say an operator A commutes with any scalar B. A, B. B is a scalar, so we are not keeping hat on that. So our commutator of AB is equals to 0. Let's go for some problem. Simple problem, but essential to develop the concept. The first one, let's say, so that the commutator of two Hermitian operators is anti-Hermitian. So you have to show that the commutator of two Hermitian operators is anti-Hermitian. So let's try to prove this. Two Hermitian operators, let's say A and B are two Hermitian operators. If they are Hermitian operators, then what you can write? A dagger is equals to A and B dagger is equals to B. What we have to show? That the commutator of the two Hermitian operators. So what is the commutator of A and B? Commutator of A and B, if you can show it that it is equal to the commutator of A and B, then it will prove. Minus sign will also come because it is anti-Hermitian. So what will be this? This will be AB minus BA dagger. Now this will become, you see, dagger is acting on the product of AB. Okay, so B dagger will come first, then A dagger, minus. Now dagger is acting on BA, so it will act from the right. So A dagger, B dagger. I hope this is understood. Now using this property of Hermitian operator, B dagger is B, A dagger is A dagger is A, B dagger is B. So if you take a negative sign common, AB minus BA. This is nothing but the commutator of AB. So therefore commutator AB is anti-Hermitian. Let me give you another question. Let us evaluate the commutator of A, B, C, D. I hope you can easily do it. How can I evaluate this commutator? A, B, C and D. What you can write? So it is like this property, right? Where is that property? Yes, it is like A, B, C, where B has been replaced by the commutator of two other operators, isn't it? So we will treat this B, C in that way only. So it is at the first place. So B, C, then remaining A, D plus. Now we want to keep this BC and take out this D. So A, commutator of BC, D. Can I write it? Now let's break it apart. Commutator of BC is equals to BC minus CB. Commutator of AD, AD minus DA plus. Now again it is coming in that form. A times BC minus CB times D plus A, sorry, there will be minus, right? Commutation gives you minus, minus this one will come first. So BC minus CB A D. Is it clear till now? Tell me. Could you understand this line up to this line? Karthik, Murli, Harry is absent today. Is it clear till now? Tell me, then we'll move forward. Let's move on. So you see BCAD, Okay, you see BCAD will come. Okay, let's write it. BCAD minus BCDA CBAD. Don't change the order. Plus CBD. Just write the way it is. A, B, C, D. A, C, B, D. B, C, A, T. C, B, A, D. So BCAD, BCAD is getting cancelled. So CBDA, let's write that first. Positive term looks better. CBDA. The BCAD is getting cancelled. And what else is getting cancelled? Minus BCDA. So we have written this term and CBDA plus ABCD, this term. You see, this CBAD is also cancelling, BCDA is also cancelling. So CBDA minus BCDA plus ABCD minus ACBD. I think this is the answer. Okay, let us now move forward to uncertainty relation between two operators. We have already talked about this uncertainty relation before, and there we told that we have to do it in terms of operators. So here let us try to explore that. Uncertainty relation between two operators. So we have already defined the expectation value, right? So let A cap average, or this is the expectation value of A, and B cap, when we are writing inside the arrows, it defines expectation value. So let A and B denote the expectation values of two Hermitian operators. Hermitian operators, let's say A and B, with respect to some normalized state, with respect to a normalized state psi. Normalized state ket psi. So mathematically, how will you write expectation value of A? This is psi A psi divided by psi psi. It is normalized, so psi psi is 1. That is why we are writing this. And expectation value of B, it is psi B psi divided by psi psi. Psi psi is 1, so that is why it is this. Now we have, let's say for uncertainty, we have to find out delta A, the error in measurement of A. Let's say, let's take a square. What is the square of this? Delta A square. So to find out the delta A square, we have to find out first what is delta A. Let's talk about what is delta. This is A, this is expectation value of A. So let us introduce these two operators, delta A cap. So this is A minus the expectation value and delta B. So it is like the error in measurement of B. B minus the expectation value of A. So you can imagine it like this is the mean value. Okay, standard deviation, basically we can say. So if this is so, then we can write delta A square, it will be equals to A square minus 2A expectation of A plus expectation of A square. On the other hand, delta B square will become B square minus 2B expectation of B plus expectation of B whole square. Now if you calculate the expectation value of this delta A square, then what will happen? It is like calculating delta A square, the expectation value of this. So this is nothing but psi delta A square. Psi, this is what is the definition demands. Now taking expectation value of expectation of A square minus 2 expectation of A, and expectation of A is already there, so we don't need to do anything about it, and here also we don't need to do anything because already expectation square is there. So this is expectation of A square minus this, you see, A square expectation, and here also A square minus 2A square. So what you have? Look, A square expectation and this A expectation square, and here is it minus 2A expectation square. So 1 is cancelling, so A expectation square. And if you do the same for delta B expectation square, so which is psi delta B square psi. So this will also give you B square expectation minus B expectation square. Does it make sense? And hence the uncertainties delta A and delta B are defined by. So what will be the uncertainty delta A? Delta A will be square root of delta A square. So it is nothing but a square root of A square average minus A average square. It is like that. And delta B is defined in a similar fashion, delta B cap square B square expectation minus B expectation square. So simple mathematics, pure mathematics. And from this we can get back the general uncertainty relation, which we have told you in the uncertainty relation class, uncertainty class, that delta square delta b square greater or equals to 1 by 4 expectation value of minus I into commutator of AB whole square. Okay, so that thing you can get by doing a little bit of calculation. You will get the product delta A delta B. It will be greater or equals to, this will come out to be greater or equals to half times expectation value of the commutator of A, and this directly corresponds to the general uncertainty relation. I think this is enough for today. We'll start with function of operators and our matrix approach in the next class. Maybe 1 or 2 more classes required. We'll try to cover it by 1 class. It may take 2 classes as well. Let's see. So I think this lecture was very crucial because operator is mainly used in quantum mechanics. So on the next day we'll go for function of operators. Till then, bye bye. Take care guys. Thank you very much. If you are new to this channel, please subscribe the channel and don't forget to press the bell icon. Bye.